Welcome to the Deep Dive, the show where we cut through the noise and get straight to the core of what really matters in complex topics. We all face this constant avalanche of information, right, every day. It's easy to feel overwhelmed, wishing there was some kind of shortcut to truly understand what's critical. Today, we're diving into something pretty fundamental, something that underpins almost every digital experience you have. Have you ever stopped to wonder how the world's biggest tech companies build those, incredibly reliable, massive systems we all use every single day? Think about the apps that just work, flawlessly scaling for millions of users. Well, there's a specialized discipline making that possible. It's called platform engineering. Our mission for this deep dive is to unpack the core principles, the practices behind building and operating these large-scale software platforms. We're talking software as a service, SaaS, and platform as a service, PaaS specifically. We want to give you a clear, kind of actionable understanding of this crucial discipline, show how it solves very real development challenges, and lets companies scale, globally. And this deep dive, it's built on insights from Platform Architect's Handbook, Building SaaS and PaaS at Scale, and Platform Engineering, Principles, Practices, and Reliability. Let's get started.
Yeah, it's an area that's become absolutely essential. It directly addresses the escalating complexity you see in modern software development.
That's a great point. And for a long time, many of us thought DevOps was, well, the ultimate answer. It definitely succeeded in breaking down those walls between dev and ops teams, really aimed to speed things up. But maybe unexpectedly, it often pushed a significant operational burden right onto the development teams themselves. Suddenly, developers weren't just coding features, they were grappling with this huge ecosystem of complex tools for infrastructure, monitoring, deployment. It created a new kind of friction, didn't it? This sort of mental overhead that actually started to slow them down.
You've absolutely hit on the core issue there. That increased cognitive load for developers meant they were constantly context switching. They were trying to master not just their app code, but also complex cloud infrastructure, monitoring tools, all these pipelines. That mental overhead, it drastically slowed them down. It often led to burnout, diverting focus from the core business features. So this environment was really the perfect crucible for platform engineering to emerge. It doesn't replace DevOps. I think that's key. Instead, it scales its principles across an entire organization. And it does this by treating the internal development infrastructure as a first-class product. The fundamental goal is to dramatically improve developer productivity, reduce that cycle time concept to deployment, and accelerate speed to market by abstracting away all that underlying complexity. The platform team essentially provides this stable, secure, and incredibly efficient foundation for everyone else.
Okay, so the platform team delivers this foundation, and the main thing they produce, the thing developers actually use, is often called the Internal Developer Platform, or IDP. This isn't just a random grab bag of tools, is it? It sounds more curated.
Exactly. It's curated, cohesive, and often a self-service layer sitting right on top of the organization's whole tech stack. And central to this IDP is a concept called the Golden Path.
The Golden Path, right. What exactly is that?
The Golden Path is basically a guided, well-supported, standardized workflow. It represents the organization's sort of tried and true best practices for building, deploying, operating a service. So for instance, imagine a developer needs a new microservice. Instead of them needing to figure out all the complex details, secure network setup, CI/CD integration, where to set up monitoring, the Golden Path within the IDP automates all that for them, based on established secure standards.
So it paves the way for them.
Precisely. And it's worth distinguishing, too. Sometimes people see a developer portal, like Spotify's Backstage, maybe. That's often just the UI, the gateway. The IDP is the actual underlying platform providing all those powerful capabilities and automations.
That makes a lot of sense. So beyond just making developers' lives easier, which is a huge win, obviously, what's the strategic business case? Why should an organization invest heavily in platform engineering? What's the bottom line impact?
Right. And what's truly fascinating here is how these aren't just technical niceties. They translate into direct, measurable business advantages. First, you've got velocity. By giving developers these self-service capabilities through the IDP, you eliminate manual handoffs, you stop the endless ticketing queues, you drastically cut the time it takes to get new features and apps out to users. That directly impacts time to market.
Faster delivery. Got it.
Second, a significant boost in reliability. The standardization baked into an IDP ensures consistency everywhere, dev, testing, prod. This minimizes human error, leading to far more stable, predictable systems.
Okay. Consistency equals stability. Makes sense.
And third, governance. A mature IDP actually embeds things like Security, compliance standards, think SOC2, GDPR, even cost management right into the workflow. This is often called shifting left, these critical non-functional requirements. Handled early, automatically, it allows robust control without slowing developers down. The platform itself becomes the enforcement point for these critical policies.
Wow. So it makes those often scary compliance and security tasks almost seamless.
That's powerful. Okay, now that we understand why platform engineering is so vital, let's talk about the landscape. We hear terms like SaaS, software as a service, and PaaS, platform as a service, thrown around constantly. To clarify, I think maybe a simple housing analogy might help here. Like, imagine on-premises. That's like building your house totally from scratch. You own the land, lay the foundation, manage utilities, plumbing, furnish every room yourself.
Right. Total control, total responsibility. Then you have infrastructure as a service, IA. AWS EC2 is a good example. That's more like renting the land with utilities hooked up, maybe a basic foundation. You get raw servers, storage, networking, but you're still managing the OS, all the software layers, your actual app, the data.
Exactly. You build on top of the basics. Then we move to platform as a service, PaaS. This is like renting a fully furnished house. Maybe the landlord provides some tools. Think Heroku, Google App Engine. Here, the vendor manages everything below your application. Runtimes, middleware, OS, virtualization, servers, storage, networking. All you, the customer, focus on is your application code and its data.
Okay, much less infrastructure worry there.
And finally, software as a service, SaaS, the ultimate convenience, like renting a fully serviced hotel room. Salesforce, Google Workspace are perfect examples. The vendor manages the entire stack, the app itself, your data, all the infrastructure. You just log in and use it. You don't worry about how it's built or deployed at all.
Got it. And these distinctions, they have really profound architectural implications, don't they? If you're building a PaaS, your direct customer is the developer. So your architecture needs to focus really intensely on supporting multiple languages, frameworks, integrating with developer tools, extensibility, all that stuff developers need.
Precisely. It's all about the developer experience. But if you're building a SaaS, your customer is the end user interacting with your specific application.
Yeah.
In that case, architectural concerns shift dramatically. You're thinking high availability, extreme scalability for potentially millions of users, elasticity to handle load changes, and, crucially, mastering multi-tenancy, serving many customers securely from a single software instance, keeping everyone's data separate. That's key.
Right. Multi-tenancy. That sounds complex.
It is.
So connecting this back, it seems like the lines between building SaaS and PaaS are getting pretty blurry. If you want to deliver a world-class SaaS product to millions of external users, your organization probably needs to first build a really high-quality, PaaS-like internal platform for its own developers. The skills aren't just related, they seem interdependent. Is it fair to say that if you're building the next big thing for users, you're probably building a platform for your own team first?
That's the core insight, absolutely. You really can't deliver a world-class product externally at scale without first empowering your internal teams with a world-class platform. Now, building on that, let's talk about how we actually architect these systems for that massive scale. Looking at the shift from, say, monoliths to microservices.
Yeah, many incredibly successful products started as monoliths, right? Initially, that approach offers simplicity, single code base, easy to get going, rapid initial development. But as they grow, oh boy, that simplicity becomes a major liability. Components get tightly coupled. Deployments become these incredibly slow, risky release trains. Any tiny update means rebuilding, redeploying the whole thing. Hours of downtime sometimes. And scalability is inefficient. If just one part is busy, the entire application has to scale. Such a waste of resources.
That's exactly the pain point microservices aim to fix. This architectural style means structuring a single application as a suite of small, independently deployable services. Each runs in its own process. This brings several key characteristics. First, componentization via services. Because they're out of process, they enforce strong module boundaries, much cleaner. Second, teams are organized around business capabilities, like a payments team owns their service end-to-end, UI to database. This fosters that powerful you build it, you run it mentality. Teams own their service through its entire lifecycle.
So they're not just building a project and handing it off, they truly own it as a product.
Exactly, for its entire lifecycle. Microservices also favor smart endpoints and dumb pipes. Logic lives in the services. The communication network stays simple. And critically, there's decentralized governance and data management. This leads to what's called polyglot persistence. Teams can pick the best tools for their job. Maybe PostgreSQL for one service needing transactions, MongoDB for another handling flexible data.
Polyglot persistence, okay.
But if we connect this to the bigger picture, Microservices don't eliminate complexity. They just relocate it. It shifts from a tangled monolith code base to the challenges of managing a distributed system. And that distributed system management is precisely what platform engineering helps address.
That relocation of complexity, that's a really subtle but profound shift. Okay, so when these independent services need to talk to each other, there are two main patterns: synchronous and asynchronous. Synchronous seems pretty intuitive, like a direct client-server request response, often REST over HTTP. Simple, immediate response. But what are the downsides?
The main downside is tight temporal coupling. The calling service directly depends on the immediate availability and performance of the downstream one. If that downstream service is slow or fails, the caller is directly impacted. It can cause cascading failures.
Right, one falls, they all fall.
Potentially, yes. Tools like Apache Thrift can help by formally defining interfaces clearly. Now, asynchronous communication, or event-driven architecture, is different. Services communicate by producing and consuming events via message brokers, think Apache Kafka or RabbitMQ. This promotes extreme loose coupling and high resilience. If a consumer is down temporarily, the event just waits in the broker.
That sounds much more robust, but what are the challenges there?
It definitely adds complexity and reasoning about the overall system state. You have to design for eventual consistency. Data might not be immediately consistent everywhere, but it'll get there eventually.
You're eventually consistent.
And managing distributed transactions across multiple services becomes a big challenge, often tackled with complex patterns like the saga pattern.
The saga pattern.
Yeah, it breaks transactions into smaller, local ones with compensating actions if things go wrong. A mature platform usually uses a pragmatic hybrid approach, mixing sync and async where appropriate.
And in these distributed systems, with so many moving parts, failures aren't if, they're when. So you have to design for them, right? From the start.
Precisely. It's a core principle, anticipating failure. One critical pattern here is the circuit breaker.
Like a fuse in your house.
Exactly like that. If a downstream service, say a payment gateway, starts failing repeatedly, the circuit breaker in the calling service trips, it opens. Subsequent calls fail immediately, without even trying the network request. This stops endless retries overwhelming the struggling service. It prevents a single failure cascading through the whole system.
Smart. So it protects the rest of the system.
Yes. After a timeout, it goes half open, letting a few test requests through. If those succeed, it closes and resumes normal traffic. If not, it stays open.
Okay, designing for failure, building resilience. But how do we build that foundation reliably, consistently, every time? That brings us to the next fundamental shift. Infrastructure as code, or IAC. This isn't just a new tool. It sounds genuinely transformative. What exactly is IAC?
Infrastructure as code is, well, it's the practice of managing and provisioning your infrastructure servers, networks, databases through machine-readable definition files. You treat infrastructure like software. The core principle is that it's declarative. You define the desired state you want. I want 3 web servers, this load balancer, this database config. The IAC tool then figures out how to get there and maintains it.
You declare the what, not the how.
Exactly. And the benefits are profound. You get automation and speed, eliminating slow, error-prone manual setup. Huge reduction in human error. Critically, it ensures consistency and reproducibility. It's the single source of truth. No more works on my machine problems across environments.
Ah, the classic developer problem.
Right. And because it's version controlled and like software, every change is tracked, auditable. Rollbacks are incredibly easy if something goes wrong. The real genius, the core insight, is achieving idempotency, meaning you run the same script 100 times, your infrastructure ends up in the exact same desired state. This isn't just speed, it eliminates configuration drift. That sneaky way manual systems change over time, ensuring production is always precisely what you expect.
Idempotency. That concept is really powerful. So if I'm looking to adopt IAC, what are the main tools I should consider? How do I choose?
2 of the biggest players, especially in the cloud-native world, are Terraform and Pulumi. And the choice isn't just syntax. It's really a strategic decision about your engineering culture and who manages the infrastructure. Terraform uses HCL, which is a proprietary domain-specific language. It's purpose-built, often simpler for pure infra tasks, but limited in general programming features. Pulumi, on the other hand, lets you use general-purpose languages you likely already know: Python, TypeScript, Go, C#.
Using familiar programming languages, that sounds like a big deal for application developers.
It absolutely is. With Pulumi, developers get full IDE support, access to existing code libraries, standard testing frameworks they already use. It feels more integrated. And on state management and security, Terraform often needs more manual setup for its state file and stores secrets in plain text by default. You need other tools for encryption. Pulumi usually manages state via its cloud service and encrypts secrets automatically. That can be a big operational and security plus.
Interesting trade-offs there.
Definitely.
Yeah.
So it's about, do you want a specialized infra team using a DSL or empower app developers to define infrastructure alongside their kin?
Regardless of the tool, how do big organizations practically structure these ISC projects to manage all that complexity?
Best practice is modularity. Think reusable building blocks. You might have a VPC module for networking, a Kubernetes cluster module, a database module. These modules get instantiated for each environment. Dev, staging, prod. Crucially, each environment needs its own isolated state file or stack. This is key. It ensures staging changes don't accidentally break production.
Isolation is critical.
Absolutely.
Yeah.
The ideal flow. Apply changes to staging first, run automated tests there, then promote the exact same IAC code to production. This structured, repeatable process is the bedrock of a robust, automated, self-service IDP.
Okay, so infrastructure is code. Next up, the engine that actually deploys the applications onto that infrastructure. Advanced CI/CD for microservices. You can't just use a monolithic pipeline for microservices, can you? That sounds like it would defeat the purpose.
You absolutely cannot. In a microservices world, the number one rule, each microservice must have its own independent CI/CD pipeline. A single monolithic pipeline building and deploying everything. Massive bottleneck. Total anti-pattern. Independent pipelines give teams autonomy, provide much faster feedback loops, build their scope to just one service, and drastically reduce the blast radius.
Blast radius, meaning if one pipeline fails, it doesn't stop everyone else.
Exactly. A failure in one service's pipeline doesn't halt others or bring down the entire release process.
Okay, but if you have, say, hundreds of microservices, how do you manage hundreds of independent pipelines without it becoming total chaos?
That's precisely where the platform team comes in again. They provide standardized, reusable CI/CD templates. These templates codify the organization's best practices, security scanning, quality checks, deployment strategies, etc. Developers consume these templates. This ensures consistent governance and reliability, but the pipeline itself stays tightly scoped to their individual service.
Best of both worlds, then. Autonomy and standardization.
That's the goal, yes.
And Docker containers play a huge role here, right? Making these polyglot microservices practical. Teams use different languages but have a consistent deployment unit.
Absolutely transformative. Docker packages an app with all its dependencies into a single, immutable artifact. It runs identically on a dev laptop, in testing and production. Your CI/CD system doesn't need to know how to build Java versus Python. It just builds a Docker image from a Docker file.
Consistent artifact. Makes sense.
And using multi-stage Docker files is a best practice too. Helps create incredibly lean, secure production images by removing build tools and intermediate layers.
And once you have these containerized services, Kubernetes steps in as the orchestrator to manage them all at scale.
Yes. Kubernetes is effectively the operating system for the cloud. It's the foundation for most robust IDPs today. Your CI/CD pipeline interacts with core Kubernetes objects. Deployments describe the desired state for a service. I want 3 replicas running. Kubernetes makes it so. Services provide stable network endpoints and load balancing for those running containers. And config maps and secrets decouple configuration and sensitive data from your application images. Much easier and more secure management.
And platform teams use more advanced features too.
Oh yes. Things like namespaces for isolation between teams or environments. Role-based access control, RBAC, for fine-grained permissions who can do what. And custom resource definitions, CRDs, let them extend the Kubernetes API itself, managing custom platform components like their native Kubernetes objects. Very powerful.
Okay, so even with all this automation, deploying a new version straight to 100% of production traffic feels risky. That's where progressive delivery comes in, right, for safer releases.
Precisely. These strategies are absolutely essential to minimize the blast radius of a potentially bad deployment. Blue-green deployments are one way. You maintain 2 identical production environments, blue, current, and green, new. Verify green thoroughly, then instantly switch all traffic from blue to green. If anything goes wrong, switch back instantly, near zero downtime rollback.
Instant switch. Okay.
Then there are canary releases,
Yeah.
a bit more sophisticated. You roll out the new version, the canary, to a tiny subset of users, maybe 1%. You rigorously monitor key performance and error metrics. If all looks good, gradually increase traffic to the new version. If any issues arise, immediately roll back traffic from the canary to the stable version.
Gradual exposure, watching carefully, and feature flags offer even more control.
Absolutely. Feature flags decouple code deployment from the actual feature release. Code for a new feature can be deployed to production but stay hidden, dormant. You toggle it on or off via configuration, no new deployment needed. This enables internal testing, targeted releases to specific user groups, robust A/B testing, experimentation. Super flexible.
So these strategies, they're not just technical tricks. They basically make safe, reliable delivery the default, the golden path for all developers.
Okay, building and deploying is only half the battle, isn't it? The real test comes in, operating reliably at massive scale. This is where the art of scalability and the science of reliability really come into focus.
Absolutely. Scalability isn't something you bolt on later. It has to be designed in from the start. Fundamentally, it's about handling growing work by efficiently adding resources. Common bottlenecks in web apps: database, server CPU, network, slow third-party calls. To fix these, architects mostly use horizontal scaling. Add more identical servers, distribute the load. Vertical scaling, making one server bigger, hits physical limits. It's just not enough for web scale systems.
And scaling the database, the stateful part, that always sounds like the trickiest bit. It definitely is the most critical and challenging for stateful layers. It's usually an escalating series of strategies. You always start with query optimization and indexing. Make existing operations faster, low-hanging fruit. Then, typically, caching. Use in-memory stores like Redis or Memcache to reduce database load for frequent reads.
Take load off the database.
Exactly. When read traffic gets too high, you add read replicas, read-only copies of your primary database. But when write traffic swamps the primary, where the dataset gets enormous, that's when sharding becomes necessary. This means horizontally partitioning your database, breaking it into smaller independent pieces called shards, each holding a subset of data.
Sharding. And choosing what to shard on seems absolutely critical there, doesn't it?
It's the most critical decision. The shard key, the data used to decide which shard a row belongs to, like tenanted in a SaaS app, is paramount. A good key distributes data evenly. But understand, sharding massively increases operational complexity, especially for queries needing data across shards.
So powerful but complex.
Very much so. It's a significant engineering effort.
Okay, so you have all these distributed servers, maybe sharded databases. You need something to manage the incoming traffic effectively.
Load balancers?
Load balancers are fundamental, yes. They sit at the front, distributing traffic across your server pool using algorithms, round-robin, least connections, etc. Critically, they also do health checks, automatically route traffic away from failed servers. Combine that with redundant deployments across multiple physical locations, like cloud availability zones, and that's how you get high availability. Your service stays up even if parts fail.
Right, redundancy plus smart traffic management. Now, reliability. Failures are inevitable, so it's about tolerating them and recovering fast. What does that mean in practice?
Reliability means building systems that tolerate failures and let you rapidly detect, understand, and fix them. This is observability and chaos engineering territory. Observability is key. It's the ability to understand a system's internal state just from its external outputs. It helps debug problems you've never seen before, the unknown unknowns.
Beyond just monitoring for things you already know might break. Exactly. It rests on 3 pillars. First, logs, immutable, time-stamped event records. Great for deep dives. Structured logs, like JSON, are best for querying. Second, metrics, numerical measurements over time. Request counts, error rates, CPU use, perfect for dashboards, alerts. Third, traces, the end-to-end journey of a single request through multiple services, essential for finding latency bottlenecks in distributed systems.
So the goal is a unified view, where engineers can jump from a metric spike on a dashboard to the specific slow traces causing it, then to the detailed logs for that exact request.
That's the ideal, yes. A mature platform provides that unified view. To achieve it, you need a comprehensive observability stack. Open source options include Prometheus and Grafana for metrics, Loki for logs, Jaeger, or Tempo for traces. Open telemetry is becoming the standard for instrumenting code to generate portable telemetry data.
Vendor neutral.
Open telemetry. Good to know.
And this leads to observability-driven development, ODD. Developers instrument code as they write it, asking, what will I need to debug this when it inevitably fails in prod?
Thinking about failure modes from the start. Exactly. And to truly prove that resilience, there's chaos engineering.
Ah, yes. Netflix's Chaos Monkey. But it's not just random destruction, right?
Far from it. It's a highly scientific process. 1. Establish a steady state, a measurable metric showing normal behavior. 2. Form a hypothesis about resilience. If a payment pod dies, error rates spike briefly but recover in 30s, no transactions lost. 3. Intentionally inject failure, controlled. Terminate a server type, add network latency. 4. Verify the outcome against the hypothesis. Does it behave as expected? If yes, great. Confidence up. If no, you found a weakness to fix.
Find the weakness before your users do.
Precisely. And this raises an important point. If a team is afraid to run a chaos experiment, they've already identified a fragile part of their system needing attention. It's about finding weaknesses proactively.
That proactive approach sounds like a game changer. Okay, let's tie all this together. A tangible example. How would an expert architect apply everything we've discussed to build, say, a scalable, multi-tenant, collaborative note-taking service? Let's call it Tiny Sauce.
Right. We'd start with phase 1, architecture and system design. Decompose tiny saws into microservices. Maybe an AP gateway, auth service, tenant service, note service, core function, and an async billing service. Crucial early decision. Design tenanted into all tenant-specific data from day one. Prepares for future sharding. We might choose Go for services, PostgreSQL for the database, React for the front end.
Okay, decompose. Then phase 2, infrastructure and CI/CD.
Use IAC, Pulumi, or Terraform. Provision everything declaratively. Manage Kubernetes, manage PostgreSQL like RDS, secure VPC networking, object storage for backups. Critically, totally separate, isolated environments. Dev, staging, prod.
Yeah.
For CI/CD, the platform team provides a standard pipeline template, GitHub Actions maybe, one for each microservice. On commit, it auto-runs tests, scans vulnerabilities, snag perhaps, builds a lean multi-stage Docker image, pushes to a registry, then automatically deploys to staging using a canary release, maybe 5% traffic first. Production deploy needs manual approval, but uses the same safe canary strategy.
Consistent, automated, safe deployments. Got it. Then phase 3, scaling and reliability.
Database scaling plan starts simple. Primary RDS, one read replica. Define clear triggers for when sharding is needed, probably using that tenanted as the shard key. An application load balancer in front of Kubernetes handles TLS, distributes traffic, full observability setup. Prometheus Grafana for metrics, OpenTelemetry Jaeger for tracing, structured logs collected centrally. Get that unified view.
And finally, phase 4, proving production readiness, the real validation.
Absolutely. Rigorous load testing on staging with tools like K6. Find bottlenecks before launch. Comprehensive security compliance audit. Check TLS, data encryption at rest, in transit. Strict least privilege IAM policies. And crucially, a specific chaos experiment. Hypothesis. If tenant service is unavailable, note service calls fail, 503, AP gateway circuit breaker trips, auth service is unaffected.
Test the resilience.
Exactly. Test it by deliberately terminating tenant service pods and staging. Then verify outcomes by watching Grafana dashboards, tracing tools. Did it behave as hypothesized?
This whole systematic approach, layer by layer, it really drives home that building a world-class SaaS basically requires building a world-class internal PaaS first.
Wow. What a comprehensive journey we've taken today. We started understanding why platform engineering really emerged, how it's the essential evolution of DevOps freeing up developers. We dove into architectural shifts from monoliths to resilient microservices, saw the foundational role of infrastructure as code, the power of advanced CI/CD for safe delivery, and we wrapped up exploring how to master production ops, sophisticated scaling, deep observability, and that proactive science of chaos engineering. Yeah, it's clear this isn't just about building software anymore. It's about building these highly resilient, efficient systems that empower developers to deliver business value at, well, an unprecedented scale.
So, for you, our listener, here's a thought to chew on as you go about your day. Think about your own workflows, your projects, even outside software. What part of your personal information system could benefit from being treated like a first-class product for your own efficiency? You know, like an IDP. How might you apply principles like designing for failure or progressive delivery in a non-technical way to make your own processes more robust, less prone to unexpected hiccups? Thanks for joining us on this deep dive into platform engineering. We hope you feel a bit more informed, maybe even inspired to build your own golden path to efficiency. We'll see you next time on The Deep Dive.